Hi, I'm Dr. Alexander NGENZI from University of Rwanda College of Science and Technology, Department of Computer and Software Engineering. We are going to discuss about the circular convolution. And remember last time when we were discussing about the circular convolution, we said suppose if we have two signals, you bring that element of just combine them. It's like summation, but it looks like a multiple. It looks like x in between the signals. So this is what we are going to discuss in the next 30 minutes, and it's going to be it's like the continuation of what we saw last time. So having the signal, I remember we discussed the convolutional sum, and this is not going to have a big difference. It's going to be like the same. We are going to start to discuss one by one. Now we are going to discuss the circular convolution. Using this DFT or DFT circular convolution. What does it mean to use this circular convolution? Remember, when we deal with circular convolution, we are talking about the circle. So it is going to be cyclic. It's going to rotate from the origin of the circle. So in this case, you can convert the time domain using circular convolution of any frequency, any given frequency domain. And also you can also use IDFT. That's why we use IDFT to get the vice versa, the other way around. So in this case, you remember when we were discussing about the circular convolution, we will have like two signals. For example, we called it N and M. Suppose you have signals, signal elements M and N, and just putting it in the equation, we will have, remember, we'll have x of k, for example, given k, or x of m minus any value. K can range from m. K can range, for example, from n minus m. In this case, you can just put it there. It's going to be x of n, remember, 0, n minus 1. Then in this case, we are using our signal. Signal 1 is going to be m, of course. Signal x is going to be m, then multiplied by y into n minus m in this case. So you can pull out. So the first signal is this side, and another signal is this one. So, and this is also this can be the resultant is going to be big X of k, which can be this side, then multiplied by the x of y into any value. So it's going to be big Y and big X convoluted together in this side. So this is a convolution sum that you can put it here. But it is still early to just indicate it. Just take it like x of k into y of k, k in this case. So this is the resultant format. So suppose if we want to do the convolution, then if it is a cyclic convolution, you are going to add it there to show that it is a convolution sum. And these signals, remember, we discussed about the periodic signals and aperiodic signals, where we were talking about the periodic signal having a fixed point where you are going to determine the change or the variation of your signals. And also, we discussed about the aperiodic signal where it doesn't follow any rhythmic change. So the change doesn't matter where it begins from. So in this case, you can have such kind. So these are like periodic signals. So this is a periodic signal that you can determine such kind of results. So you have this you can see it doesn't follow any order. But for a periodic signal, you can have also different convolution sum that you can obtain. Remember, the convolution is going to rotate just toward just from the origin of the circle, given, for example, any value here. So it's going to rotate according to any value in this case. So it can begin from the point of origin, depending to which values that you have. Remember, this is real values and this is imaginary value. In this case, this is from, for example, you can follow negative infinity to infinity. In this case, it depends how many values that you can obtain in this case. So this is what, whereas the other symmetric, you can use the cosine and sine value, but here it is imperative that you have to show the point of origin. So suppose if we have two signals, for example, x of x1 of n and x2 of n, and you want to obtain the x3 of n in this case. So you have to convolute first these ones. It's going to be x of 1 of n. Just putting the other value of convolution sum in this here, x of 2 of n, then you can either get the x of 3, x3 of n in this case. So this circular convolution just exists in two, so you are just joining two signals at the same time. So in this case, our signals may be m or n, depending to how we have explained them. So in this case, you can substitute the values of, for example, the x and y. For example, if the other signal, for example, this one was y, then you can easily determine them. In this case, you can just put it in this form. You can use m beginning from 0, from n is equal to 1, remember, but you have two signals to x, x of m, in this case, multiplied by x of 1, then multiplied by another signal, which is n minus m, which is in this is x, this can be y, can be anything, and in this case is going to be the big portion of n. So this is the value of how you can calculate them, and therefore these values can be computed using the convolution sum. The symbol presenting the convolution sum is going to imply the frequency domain multiplication, as I showed you in this case, and the resultant here is going to be so this is going to be big X. For example, the x1 of n convoluted by x2 of n is that one, but also it can be put in the format big X of 1 of k, for example, convoluted by big X of 2 of k, for example. Then you get the y of k, or any resultant value x of 3 in this case of k. So this is the corresponding value of the way how you can obtain their corresponding values of frequency. So it doesn't make any difference compared to what you have seen. It is the same thing, but in this case we are trying to bring any aperiodic signal, the signal that are not alike, for example, doesn't have a fixed point or fixed value, then you supply them according to their point of origin. And remember, if you want, for example, to get a reduction of m, for example, you use inverse discrete Fourier transform, which is the other way around. And in that case, you can have, for example, you remember the other formula of 2 pi to n summation of yeah. If you remember how we calculated them, you can easily transfer this one. So this one can be vice versa, and then it will be 1 over n, because if you have n, its inverse is going to be 1 over n, and then you transfer. So in this case, for inverse discrete Fourier transform, now we are looking for small x of n, and then it's going to be 1 over n, and then summation of, for example, n is equal to 0, big N, like that. But in this case, the terms are going to be big X, because we are having frequency, but we are looking for discrete value. So this is the foundation of what we are discussing about the convolution sum. Now we are going to see the methods of how we can have, how do we calculate the convolution sum? How do we begin? How do we start? Now, what are the methods, or what are the steps in calculating these ones? So we have like 3 steps or 3 methods that we can use. We have number 1. So in this case, we are calculating convolution. Okay, in this case, is going to be circular convolution. In this case, this is going to be circular convolution. So how do we calculate them? We have 3 methods. So number 1 is graphical method. Number 2 is going to be using the DFT or IDFT, and number 3 is going to be using the matrices. This one also we have also covered them, but also we want to show it where possible, so that you can use also matrices. So the matrices are very common in computers, using both the sequences that have the same numbers or the same samples. So these matrices are used when you have a number of samples and you want to calculate the endpoints. So in this case, we are going to discuss one by one, beginning from the graphical method. For example, if we have a circular convolution of these values, for example, a point of origin, for example, and you have xn in between, in this case, you can have numbers circulating in this point, the symmetric value. This is x of 2, for example, the x of 6, if you have 6 values, for example, in this case, this x of 1. So this is the point of from the point of origin. This is going to be the symmetric value. So that's the x of 4, this value, and then this is the x of 3, and the other one is going to be x of 5, and the other one, for example, is going to be x. Okay, this point is going to be x of 7. So you have, for example, 8 values, for example, from 0 to 7. So this is a circular convolution, but for example, if it is the n, if x of is n minus 1, so if x is x of minus n, then it can be the other way. So if you do this, it can be anti-clockwise. The other one can be clockwise, and in the other case, but if you want to turn the other way around, then the values are going to change. In this case, where, for example, this one can shift the other thing, they are just the anti-clockwise, remember, clockwise and anti-clockwise. And in this case, where it was x of 2 is going to be x of 6, and here is going to be x of 2. And where it was x of 5, in this case, is going to be x of 3 in this case. This one, the point of origin maybe is going to be the same. Remember, this is going to be the same. And on the other side, x of 7, and then x of 1, of course, and x of 5. So it is so suppose if we are given number in this case, it is showing the reverse of the x of n and x of n minus n. So it is a reversal. This that we are doing is called a reversal sequence. A reversal sequence of our terms of all our samples. So this it shows the number, the way how you can twist them using time reversal sequence. And the time reversal, we have not talked about these ones, but you will at the end of this portion, you will have you would have understood the concept of each one of these ones. So remember, it is circular, so it can circulate if it's a time reversal sequence, or it can be the other way around. So suppose if we have two signals, the sampled signal, if we have x of 1, in this case is going to be x1 of n is going to be 2, 1, 2, 1. And we have x of 2. Now we are going to see the circular convolution of the signal. It's going to be 1, 2, 3, then 4. So you can see at n1, the big n1, at n1 is equal to 4, and also at n2 equals 4. So the number of n are becoming 4. And this one, for example, is going to be periodic at this case, because after one number, it becomes the other number, so it is going to be periodic. After 2, then it jumped and it becomes 2. Then after 1, it jumps 2 and then becomes, this is periodic signal. The x1 of n is periodic signal. Periodic signal. So in this case, you can determine whether it is periodically. After this, the number repeats itself, and that is the big, I mean, the definition of a periodic signal, that the number can be, the sample can repeat at a particular point, at any fixed point. So, so that was the time reversal, but also you can have what we call folded. Folded sequence is the other sequence whereby you find taking some other direction on this end, then it can just be reversed from their point of origin. So just showing the direction. It can just easily show the other one where we say the counterclockwise and clockwise direction. So that's what we call a folded sequence. Folded sequence. So we are going to discuss this one. in our next slide.